Wetlands are one of the most important ecosystems on the planet for helping to clean up water. We call them nature's kidneys because it takes pollutants and sediments out of the water and it cleans it up. And yet for hundreds and hundreds of years, our ancestors did nothing but drain wetlands because they called them swamps and mosquito infested, et cetera, and then they'd plant crops on them. Okay, so what's the ecological function of a valley bottom wetland? The banks are low. Water will go over bank very quickly, spread over a great distance, hit that vegetation, and spreading over a great distance and getting the roughness of that vegetation, the water velocity plummets. So if you look at the photograph in the bottom right-hand corner, that brown silty clay that overlies that black strip near the bottom is only about 200 to 300 years old. And it shouldn't be there.
In the mid-Atlantic region of Pennsylvania, Maryland, Bob, Walter, and I had begun to notice that there were high eroding banks in many places, and we couldn't tie them with modern land use. And at each of those sites, we noticed there was an old mill and an old dam.
For our ancestors in the 1700s, 1800s, 1900s, water power was king. It's as important to their society as oil and gas is for us today. They were building dams to create ponds, these mill ponds in Lancaster County. They were filled to the brim by the time of the Civil War. And thousands and tens of thousands and hundreds of thousands of tons of sediment is now stored here in these valley bottoms, and it shouldn't be there.
We got LIDAR data in 2008, and we were able to then find those dams from airborne LIDAR, which is laser mapping of the Earth's surface. So we began mapping them over a large region.
After every storm, our streams look like they're running chocolate milk. The big question is, where's that sediment coming from? And prior to our work, the traditional answer would have been, well, it's from the farm field. I challenge you, look around this watershed and tell me where you see any bare soil. So that was a big eye-opener for us. And so we started working with a local engineering firm called Land Studies. They said, well, what if you go in and you remove that legacy sediment and we try to restore that buried wetland? We thought, brilliant, great idea, let's give it a shot. Only we want to monitor it scientifically for at least 3 years, maybe 4 years, before we go in and restore it, and then we'll continue to monitor it after the restoration.
The idea is that if we can map an area and understand everything about it, we can suggest the best kind of restoration project to put on that area.
5 or 6 feet of silt on a black wetland soil, which is at groundwater level, is not really a floodplain, especially long after a dam has breached and the channel is deeply incised. So planting trees, at least, in such an environment can be challenging because they don't get wet very often. The trees are way up high on top of the silt, and much of the legacy sediment is silt, it's fine-grained, and it dries out in the summer. Very little could survive other than some of the invasive species, such as multiflora rose, did well. So at that site, we suggested, rather than trying to get things that could survive in a wet environment because it didn't get wet very often, why not remove the sediment and lower it? Now in other places, we can actually identify where the legacy sediment is thin, and that might be a good place to put in a more conventional tree-type planting. In others, where it's much higher, we might advocate that remove some of that sediment, at least enough to get more frequent overbank flow, and then put in more wetland-type plants.
The restoration was completed November of 2011, and so in not even 2 full growing seasons, we started to get tremendous response of the ecosystem, of the vegetation. The plants were chosen based off of that seed library, I call it, that we got out of that buried wetland. It informed us what wetland species existed here naturally. One of the big improvements of this water was the reduction of the water temperature. When we removed this legacy sediment, we daylighted multiple springs that hadn't seen the light of day in over 300 years. And we see an annual reduction in the suspended sediment load in the downstream gauge of over 100 tons of sediment. And that's over a 3,000 linear foot restoration. we reduced the annual sediment load by 100 tons. That's enormous.
At our project sites, we have a couple different ways of monitoring. We can fly drones pre and post restoration so that we can see and quantify exactly how that landscape has changed. We also have various instruments that we have in the field and GPS units that we can go out and record these kinds of data sets.
So the future, we see great potential now. So many of these legacy sediment removal projects have been done, and one in particular, Big Spring Run, with intense monitoring going on now for a decade, pre and post restoration, that we've been able to show this is successful, it's sustainable, it's effective, it's cost effective, and it meets so many needs for meeting the total maximum daily load goals and for improving ecosystem benefits. And as developers look at a site, they can actually remove historic sediment and create a wetland and get all their stormwater benefits and even more, some of their nutrient reductions that they might need, and the townships can benefit from that. What we see happening now is more and more of these projects are being put in the ground.